Then it's my great pleasure to introduce to you Andreas Winter. I think many of you know him, but I introduce him nonetheless. So he did his diploma in Berlin at the Freie Universität, then his PhD under the supervision of Alswede in Bielefeld. Later, he was a lecturer at the University of Bristol, and then appointed also a professor at the same place. Had like a joint affiliation with the University of Singapore as a visiting professor, and finally moved to University Autónoma de Barcelona, again as a professor. And that's where he still is. He's also the recipient of a long list of prizes. Maybe the most important one, I think, for at least for many of us is here the IEEE Best Paper Award for the quantum reverse Shannon theorem and resource trade-offs for simulating quantum channels, and the lately prize by the International Quantum Award, the Alexander von Humboldt Fellowship, and the Hans Fischer Senior Fellowship at TU Munich, which is why he can visit us often. Okay, and now we can hear us talk about entanglement-assisted communication. The stage is yours.
Okay, thanks. I hope the mic is still working. Thanks for the very nice introduction. It's to deflate it a little bit. It's good to be back in the city of Gauss. No more words about how many awards he won. So yeah, so my brief was to give a sort of an overview talk about what I know about entanglement-assisted communication, which surely is just, I mean, like what I'm going to talk about in this presentation is surely just a very small section. It's strongly biased by what I know, what I like about this field, and by fundamentally by the fact that I'm a theorist. So I like, to play with the concepts. Okay, yeah, so I'm starting with entanglement. Yeah, so entanglement, as hopefully everybody here knows, this in the history of quantum physics, this goes back to the famous paper by Einstein, Podolsky, and Rosen, the supposed incompleteness of quantum theory, and the subsequent analysis of Schrödinger, both from the year 1935, so it's quite a long while ago. And so back then, people made already very strong pronouncements about the important role of this in quantum mechanics. Of course, we think it's still very important in quantum information processing, like quoting from Schrödinger's papers about entanglement, where he actually introduced this word. So he called it not one, but the characteristic trait of quantum mechanics, which marks the departure from the classical thinking. And Einstein coined this expression of the spooky action at a distance, which is not like, actually I put this here in German so that I can reflect a bit on the linguistic finesse of this, because it's not like spooky action that sounds like some horror film or something. You think like a skeleton or something, which and it's really true. Like, I mean, in popular texts, apparently the impression is, oh, this entanglement is sort of crazy. Einstein wanted to express his recoiling from this, but this is not what this says here. This is about the following. Well, actually, let's get over this, because so I can get to how entanglement doesn't work and to explain the spooky action at a distance. Well, okay, so in the original paper by EPR, you have an entangled state between two parties. I choose just a 2-qubit singlet state. And then one of the parties measures and gets an outcome, which of course is random. So if the measurement is this 2 outcome measurement here with a vector and on the orthogonal vector, you can get plus or minus outcome with each of the probability 1/2. And then the other side, I mean, according to the rules of calculus, Copenhagen, shut up and calculate, instantly the state of the system collapses. We don't care so much what happened to Alice, because that's measured anyway and is the eigenstate of the system. But at the same time, also Bob's state will collapse to the orthogonal state, because they're in the singlet state. And so that's this spooky action at a distance, because supposedly something subterranean happens and influences something far away. But of course, as Einstein very well knew, and Schrödinger and many other people at the time, Bob still doesn't get a signal. It's not like Alice can tell something by this procedure to Bob, despite some other people more recently. I think this Herbert is from the 70s or 80s, the so-called flash device. they thought they could use this effect to signal instantaneously at arbitrary distances. It was just a question of time to develop it, and this kind of thinking, it provoked Wouters and Zurich's and other people's no-cloning theorem. So the reason why it doesn't work is because without the information of the outcome, it could have been also the other state with equal probability, and then Bob, of course, also after the measurement and without any kind of actual signal passing, Bob still has just this equal mixture of the two orthogonal states, which is the same identity that he had before. And so, so this is a spooky action, right? Like a spectral apparition that you can see something, maybe you imagine something, but you can't touch it, and it can't touch you. That's how a ghost actually works, right? It doesn't do something to you. It's just spooky. So it's kind of this detached from the actual world. So yeah, so the topic of this talk and of this whole entanglement-assisted communication is by itself, entanglement doesn't allow you to communicate. It represents some kind of correlation between two parts, and as such, if you can communicate in some way, entanglement can enhance this communication. And so the very first example I want to show, which maybe also historically is one of the very first and most important, that's dense coding. That's apparently, according to Bennett's telling of the story, this goes back to Wiesner's ideas from way before, and then in '92, finally Charlie Bennett convinced him to publish this. And so I guess, again, I believe many people here will know this. The entanglement is still shared between two parties. This is now a maximally entangled state here. I think I chose a different one in the Bell notation. And Alice can send 2 bits. So she has two, alpha and beta are each 0, 1. And she applies these kind of, according to this prescription, a Pauli operator, and then sends the 1 qubit that she has to Bob, and then he has 2 because he had already the other qubit, the other spin from the entangled pair. So he can make a Bell measurement on the entangled on the 2 entangled qubits, and can recover alpha and beta with probability 1. And so yeah, so that's very nice. But I mean, on the other hand, you say, well, I mean, there are 2 qubits in the game already, right? So maybe this is not so surprising. Of course, it's still surprising because this 1 qubit could have been sent before, or could have even been sent from Bob to Alice, and so it sort of doesn't evidently contribute to the communication. Yeah. So anyway, so in this notation that Bennett popularized, these kind of resource inequalities, if you have the capacity of 1 qubit and the capacity of 1 sharing one e-bit, 1 EPR pair, then you can send 2 classical bits. Of course, for a fair comparison, you need, so now I'm going back to like what happens if you have no entanglement, so you can quantify the advantage. For a fair comparison, you need to know what the unassisted information capacity is. So like how many bits can you send if you have just a single qubit and nothing else? And of course, well, what you can do is you can prepare orthogonal states, and because they can be perfectly distinguished at the output. And so with 1 qubit, you can send 1 classical bit. And that's optimal in a sort of intuitive way because, well, at least if you want perfect discrimination, because if the output states have to be perfectly discriminated, well, they have to be orthogonal. And in a 2-dimensional Hilbert space, there are only up to 2 orthogonal states. Well, okay, so that's kind of the other thing, the information theory. So let's think about it in more Shannon theoretical terms. What happens, what can we say something about the capacity of the noiseless qubit? Well, this would mean that we are actually communicating over many uses of this channel. So that we have n qubits here, and the sender can prepare an n qubit state, and the receiver can measure. And like in Shannon theory, always we abandon this idea of the perfect performance, but we allow some small error probability. And well, okay, some people call this the Holevo bound. Actually, there's a simple direct argument that shows that this number of bits that you can send here, so the log of this number of messages, this can be at most n plus some constant that depends on the error probability. I don't know if I have the proof here, but it's kind of sort of a refinement of the Holevo bound, which says, okay, you just calculate the mutual information for this channel, which is easy because there's no noise. and you get 1 because it's log 2. Yeah, so this kind of, I'm just doing this sort of as an introduction, like about this reflection. Okay, we have a quantum advantage, right? So we have the noiseless qubit channel. We can send 1 bit through each use of the channel. But if you have entanglement, or if you have the right kind of entanglement, we can send 2 classical bits. And so now to quantify the entanglement advantage, there are sort of 2 sides to it. So I call this the absolute limit and the no free lunch side. These 2 bits these 2 classical bits per qubit sent, this is optimal even if you have arbitrary entanglement. So you cannot beat that. The Bennett-et-al. Protocol, the Bennett-Wiesner protocol is optimal. Doesn't matter what entanglement you have. You can only double the capacity if you want. So this is this here. If you send n qubits, but you have arbitrary entanglement, whatever it is, whatever the protocol requires, you can only transmit 2n plus this constant, which comes from the error probability many classical bits. And then there is this no free lunch, which is, well, if I have too little entanglement, well, I also don't get a huge effect. Yeah, so if I can send n qubits and I have a state of Schmidt rank 2 to the k, for example, k such singlet states, so k maximal entangled states of qubits, you can only transmit n plus k classical bits. Yeah, so there's a clear quantification, there's sort of a quantification. The more entanglement you have, the more advantage you get up to a point, and then it just tails off. Okay, so here's a bit of explanation why that is. Actually, the absolute limit, that comes from another protocol of quantum advantage, if you want, which is teleportation, that came a little bit later. If you can send 2 qubits and you have even more if you can send 2 classical bits and you have even more entanglement, then you can send one quantum bit. Yeah? So this is the famous teleportation protocol. That is, well, I guess this is kind of why we are hoping that for our future quantum internet, we are basically just have to build our infrastructure to create a lot of entanglement, because then classical communication we have already. So once we have those 2 things together, we can also communicate quantum bits. Yeah, so you can plug these 2 protocols together, the dense coding and teleportation. And if you could send more than 2n here, then you would get some kind of a perpetuum mobile of communication. You could have a bit of entanglement, and you can send arbitrary amount of communication. We can send a number of classical bits in the protocol, but that would transmit much more than n. The same number of classical bits. And that can be excluded, well, by the same kind of argument as the spooky action at a distance. You cannot increase the amount of information of a classical channel if you just have entanglement. And the no free lunch, well, that is even easier to argue, because as we observed before, well, the entanglement has to be distributed anyway beforehand, right? So in a way, the encoding is a bit of cheating, because somewhere it has to come from. So some k qubits had to be communicated before, and so we can make an argument of this. You can actually distribute the state beforehand by sending those k qubits, and then use the protocol using a total of n plus k qubits, and then Holevo tells us, well, you cannot give me more than n plus k classical bits with that. Fine. So that looks kind of fairly innocent, no? That's okay, I'll mention this briefly, but this is it's sort of a big jump, but it fits here. So later on, I will talk a little bit about the entanglement assistance of a noisy communication channel, which is the more realistic setting that the channel connecting Alice and Bob is not a perfect qubit channel, but it's a realistic channel with some characterized noise. So in that case, we have a classical capacity of the channel, so the number of bits you can send without entanglement, and the entanglement assisted capacity. And so for a long time, this actually going back to Holevo in 2001, this was an open question, how large the ratio between these 2 can become, because it was observed that even when the classical capacity is very small, the entanglement assisted capacity can still be rather large. And so depending on the dimension, on the dimensionality of the system on which the channel acts, this ratio was observed to be as large as order d, this dimension. And only recently, a collaboration from Copenhagen, Wolf et al., they showed that this ratio is actually bounded by some other function of the dimension. So this is very curious. Like I was stuck with this for a long while, and I was very happy when I saw that they could actually do something about it. Okay, let's go into this a bit more in detail. So what happens when we have realistic entanglement assist? So I'm still stuck just in this very simple game of a point-to-point channel where we have one sender and one receiver. And we have a noisy channel and a mixed state. So both of those things are supposed to be more realistic compared to the idealized perfect channel and perfectly pure state entanglement. And so if those are the resources, then this picture here, this is the general protocol. Yeah, so the protocol starts with sharing the entanglement. So this is now a mixed state between Alice and Bob. Alice has a message in mind from some set. And then depending on the message, she can apply some modulation, right? So this is not, I mean, not as in the simplest case where she prepares a state, but she has to do something to the entanglement pair, to her particle of the entanglement pair, with some, well, a quantum channel. I mean, in encoding, this is just a unitary, but it could be just another channel, even though it looks a bit questionable whether adding noise would do any good for Alice, but we just want to have a form for the most general protocol. So this is just a transformation. Then she sends the system through the channel, and Bob now has two parties, the output of the channel and what he had before, and makes a big measurement. And his task is to estimate the message, right? And we want to know how many bits can we transmit given a certain level of error. And so there are sort of the extreme cases, the one we discussed already, perfect channel, perfect maximal entanglement. We have a very important case. This is, well, this is the basic case, the baseline case. The noisy channel is general but no entanglement. And then this optimal number of bits divided by the number of channel uses. If we use the channel many times, this is the classical capacity, which has been investigated since the times of Volevo in the early 70s. And so we have a formula for this. So there is this very important quantity, the mutual information, the quantum mutual information between classical information X and quantum register B. This is Bob's information. And so this mutual information that's written down here, it's the entropy of X plus the entropy of B minus the joint entropy. So it's formally like the Shannon information. And it's all with respect to a state that is written here, the correlation between this X and the output of the channel. And so this is called, sometimes people call this the Volevo information or the Volevo capacity of the channel. But then for the classical capacity, we have to take this ungainly regularization. So yeah, so in some cases, this calculation can actually be done. For example, for the depolarizing channel, we know what this is, and it looks very much like the binary symmetric channel or the symmetric channel in classical. There is another important extreme is what we discussed before. If you have given channel and we have arbitrary entanglement, so the entanglement that you need in your protocol, any of that is given. So I don't specify the state that Alice and Bob share, but whatever. Then you get Bennett et al.'s entanglement-assisted capacity, which also has a nice formula in terms of the same mutual information, but of a different state. So what you do is you calculate a quantum mutual information between two quantum systems, and those two quantum systems are basically the two systems of the sort of entanglement you can generate through the channel. If one of the two parties prepares a state of two systems and sends one of them through the channel, they get such a state here, this identity tensor n acting on a probe state. And it's a bipartite state, and you can calculate the mutual information. And the maximum of that, this is the entanglement assisted. This turns out to be the entanglement assisted capacity. And when you go through the paper, you also get an idea of what kind of state they need. Actually, there are different proofs of this result now with different, with different raw entanglement that you use. I mean, there's not a unique one. And the reason for that is basically that we allow these small errors, like in channel theory. It doesn't have to be perfect, so we can play a little bit with the state and with the protocol. They all have asymptotically vanishing errors, and they all lead to the same famous rating. And so these are the two quantities about which what Holevo treated, this ratio, the entanglement assisted. So we have unlimited entanglement divided by unassisted capacity. And so, yeah, you can reflect again about this kind of advantage of entanglement that you have here on these two sides. So the entangled resource, you do need actually to share this entangled state before. And so that this is kind of a startup cost that has to be performed before the communication starts. And that is the entanglement entropy of that state, the entropy of the von Neumann entropy of the reduced state. That's the number of qubits that you need to send to establish the state. And there is a kind of a no free lunch that sort of an additive bound. So the entanglement assisted capacity cannot be unboundedly larger than the unassisted capacity in the additive sense. So like if there's at most an offset of the dimension of A. In fact, I would say there's at most an offset of the dimension of this here. If you fix the state, it's this entropy. And because the entropy is at most log of the dimension, that's the upper bound. Oh yeah, another case which has a long history, a surprisingly long history, but now we're entering already a domain that probably is much less common knowledge. And maybe that explains why there is this large number of references down here, because I think many people sort of discovered this and then rediscovered the same question again and again, because simply it's not mainstream enough. But it falls in the same framework. I look another extreme. The channel is the noiseless one of Bennett and Wiesner, but the state is a given mixed state, whatever, like some very noisy state. And so, so our protocol can use the entanglement, but of course could also not use it. So our capacity, which I want to denote like this, the capacity, so the limiting rate is this capacity of the identity channel assisted by rho. This must be at least equal to the log of the dimensionality, right? If I can send a qubit, I can send already 1 bit, even if I completely waste my shared resource. So there's some kind of advantage, which I want to bring out here. So there's this delta here. And this kind of has been called variously dense coding advantage. And there is a formula for that, a Shannon theoretical formula, which doesn't look very nice because, again, it's a regularization of a single letter quantity. And the single letter quantity is denoted with this crazy wedge here because it's actually a coherent information, according to Schumacher's invention of the coherent information. This is a simplified information. This is basically just the entropy of one of the two marginals minus the joint entropy. So it's the negative conditional entropy. And this is known to play a role in quantum communication and entanglement quantification of this state. And okay, so we're given the state rho, we still have a maximization of this coherent information, namely over all pre-processings. Alice can make a pre-processing of that state from, well, it lives on its own system, A prime, and it has to map to the input of that noisy channel. So this A is a d-dimensional system, I guess. So we're looking here in the limit of an asymptotically large noiseless channel. So the advantage will grow as d grows, and in the limit of d going to infinity, I get this here. And then A is an arbitrary system. So I just optimize over quantum channels here. I form again a bipartite state, all states which descend from rho by applying locally an operation, and then I can calculate this coherent information, hopefully, and optimize it. And yeah, so this, the earliest reference I found is back here, this Bose, Sugato Bose et al. In 2000, Gary Bowen, what's his name, Toya, Hiroshima, I think, also 2001, also me in 2001 was published in 2002. And then a very important paper that sort of cleaned up the whole mess, Piani and Horodetsky 2012, which already is a while ago. So a bit of reflection. I mean, this is sort of general formula, right? It's always good to think about, well, so what does it tell me about something concrete? For example, if no entanglement is present. I mean, no entanglement could mean that the state is mixed, the state is separable. In that case, because the coherent information turns out to be 0 or negative for separable states, the advantage is 0. And in fact, it's consistent. When you think about it operationally, the separable state is from the point of view of Alice and Bob, not much more than just shared randomness. So that you can explain what's going on in entire classical terms, almost. You have a quantum channel, but otherwise you've just shared randomness. And you should know from Shannon theory that having communicating via noiseless channel and having shared randomness, it doesn't increase your capacity. This is like spooky action at a distance again, only classically. And so, of course, I mean, so the looking at the properties of this coherent information, if that is 0, that has to do with the state rho being undistillable. So it could be actually bound entangled, or more specifically, one-way undistillable, because it's actually only the directed coherent information from Alice to Bob. Then this advantage will be 0. So there's there are lots and lots of states, separable and also entangled ones, where you don't get an advantage. A question you could ask is, well, I mean, can we characterize the states for which this kind of task has an advantage? Which states do you actually give an advantage of communication in this sense in a communication protocol? And so this is something that, I mean, like ever since I thought about this in 2001 or a little bit later, I thought this is a very interesting question to kind of go the other way around, to look at the state, because that's what we do in quantum information theory, like physics side. We look at those entangled states and we want to classify them or want to quantify them. So intuitively, this here, even though this number here, even though it's not actually technically speaking an entanglement measure, it does quantify something about the entanglement of the state. And so which entangled states can offer any advantage? That's an open question so far. So let's think about this a little bit during the talk. So I just want to quote yet another paper. So this is the most general case, and this was like I introduced the general setting, general noisy channel n copies and general resource state rho n copies. So this gives the rho assisted capacity of n, denoted like that. And so again, you looking at the advantage, you want to ask, so like I said, for example, for a given channel n, if rho is separable, then we get the same capacity. Again, the same operational reasoning. We don't even have to have a formula. Yeah, so you can again give a kind of an information theoretical characterization of this, but like most of them, it has this regularization here. So it's in some way, this is still a special case. This shows is like when you have a pure state. Okay, fair enough. So I want to think about the general case, which again you can make up some kind of general formula, but it's not going to be pretty. So let's think about this more conceptually. If rho is separable, this is like shared randomness, because you could prepare the state having just shared randomness. So then from that and from the definitions, you can infer that these capacities will be the same. So conversely, you could say if you have a gap, if you can prove for a particular pair of n and rho that the one capacity is bigger than the other one, this is some kind of an information theoretical, very indirect way of proving that there is useful entanglement in the state, right? And so a question that we asked with my former PhD student, Stefan Bäumel and Dong Yang, is this one. If rho is entangled, do we always have a witness like that? Can we always find a channel n such that the assisted capacity is bigger than the unassisted one? And well, so far, this is an open question. We have some partial results here, and with Minglai Tsai, we took this up in a more general setting more recently, where we also look at wiretap channels. So yeah, you have to be a bit more careful, but so I refer you to this paper where we generalize the question. Let's say it's still open, I guess. So we even with a more general kind of witness, we don't know. But I think this is a not very practical way. I don't want to sell this as like a new type of entanglement witness. Don't get me wrong. I think this is more to do with understanding what kind of entanglement is useful. And there are many results out there in more general quantum information processing that show, for example, Marco Piani has a paper from a while ago, PRL, where he shows that every entangled state, every bipartite entangled state is useful for some task. And the task is channel discrimination. You just want to discriminate two hypotheses, each of which is a noisy channel. And so you can probe those channels by preparing an input and and measuring the output. And if you have entangled probes, it is well known that you can do much better. So he says, well, what if I give you the probe? Like I prepare the probe for you, and you're lucky it's entangled. Does it provide an advantage? And well, the answer is sometimes it does, sometimes it doesn't. So his contribution was there are channels which are discriminated better using that probe than without any probe. So in that spirit, we just want to kind of enlarge the entanglement advantage. If this would be somehow, in some sense, is always the nicest, theoretically at least, if you can conclude that whatever entanglement you have, it's going to be useful for something. And so very reassuring, no? Like when when you deal with this. So yeah, let's go back to the basic protocols. So teleportation and cousins, I call this. So teleportation is this one. I mean, like yeah, it's sort of the inverse of dense coding. The entanglement state is here. Alice has a qubit state, and then she makes a Bell measurement, and that gives her 2 bits of output, and then Bob has to do the inverse unitary from the dense coding protocol. And so you could say, this is not so much an advantage. This is like a radical game changer, because obviously, I mean, this was something observed in the same paper by Bennett et al. If you don't have entanglement, and have even unlimited classical communication, you couldn't do that, because you would have to measure here, and that gives you only partial information about psi. There's no measurement you can do that allows you to reconstruct psi perfectly, because it would imply cloning. In fact, the no-cloning theorem and its development, they give you a limit of how good an approximation of psi at the output can appear if you have only classical communication, no entanglement. And you can refine this if you have too little entanglement and unlimited classical communication. Again, you get a fidelity bound, for example, an error bound. So unlike the previous discussion where we could say, oh, it's just an advantage, we have some communication, we just increase it. Here we do something qualitatively different. Yeah, that's probably true, but I still would like to sort of put it all together in the same box of quantum advantage. Yeah, so in particular, what we know is that if you have entanglement plus classical channel between Alice and Bob, this applies secret classical communication. So in fact, this is basically the idea of Eckert, that like developing the QKD protocol of Bennett and Brassard and other people. He realized, okay, this kind of everything is even simpler if the starting point is an entangled pair between Alice and Bob, and if they can be sure that they have this entangled pair in some way, which there are different ways of doing, for example, Bell inequalities, then you just measure that, and by quantum physics, this cannot be correlated with anything else. No eavesdropper can have any knowledge about this. Okay, so I just want to sort of pause here for a moment. One of the interesting discoveries of the earlier history of those times in the early 2000s is that actually it's not necessary to have a pure state. I mean, it's kind of this was almost an assumption from practical cryptography at the time. You needed to for example, for these Eckert type protocols, you needed a pure state. You needed to maximally violate a Bell inequality, and then you could infer that you had a particular state, and then you could measure it. And so by the fact that it's a pure state, it cannot be correlated with anything else, and that's the secrecy. So what Horodetsky and Oppenheim discovered in the early 2000s, like 20 years ago, is that this is not necessary. They're highly mixed states. In fact, there are states of this form. They call them p bits, private bits. That's kind of the general mathematical form with some extra stuff here. They call it the shield. And these states can be so noisy, they can be even bound entangled. I mean, they have to be entangled, but they don't have to have any extractable pure state entanglement. And so there is actually a difference between secret key and pure entanglement. So it's there's yet another resource if you want. That's why they have this name here. Yeah, so that's what I showed already. So there are states which are, well, not of this exact form, I think, but they're sort of with a slight perturbation, they can become PPT. They can be positive partial transpose, and then they're bound entangled. And so what we know, what this shows is that there's some kind of a hierarchy of properties. So the most basic one is that the row is entangled, the bipartite say is entangled. That's a necessary requirement for a row to have distillable key, but we don't actually know if it's sufficient. So this is an open question here. We don't know whether every entangled state actually has every entangled state has distillable key. But from the Horodetzky and Oppenheim result, we know that there are states which have distillable key, entangled states, but no distillable entanglement. So those are different categories of usefulness, if you want. Yeah, so I want to briefly talk also about other things. So, I mean, I talk a lot about capacities because that's kind of by professional deformation. That's kind of my first port of call. But you can think about this also differently. So here's an example of a quantum advantage, even when of an entanglement advantage, even when your communication system is classical. So in this case, the entanglement-assisted capacity is equal to the unassisted capacity. So the asymptotic capacity with small errors is the same, but the errors behave differently. And so when you have a classical channel, so this basically just a probability transition matrix, what happens is that sometimes you can reduce the error to 0. So yeah, the objective is to communicate perfectly through this channel. And so this is kind of goes back to Shannon in the 50s. If two inputs are confusable, which means that they can lead with some probability to the same output, then they may not be used in the code, both of them, because you cannot be sure when you receive that output where it came from. And so you need a so-called independent set in the confusability graph. So everything becomes graph theory. You throw the probabilities out the window. And okay, so you just need this kind of the largest code is the largest independent set, and that's a famous graph parameter, the independence number, and that leads to a capacity of the channel with 0 error. And so it turns out, well, I guess I shouldn't go into detail. So by appropriating constructions from the so-called Koch-and-Specker theorem about the contextuality of quantum mechanics, so those are sets of vectors that you can construct measurements, we could, together with Q Bidlung and Will Matthews, we could come up with channels whose 0 error capacity is increased if you have entanglement. And so this kind of, there's a whole history. So subsequently, this was also extended to the asymptotic setting. So the asymptotic 0 error capacity is a notoriously hard parameter to compute of a given channel. You can separate this from the entanglement-assisted 0 error capacity. And so what Will Matthews eventually realized, what's happening is not so much the 0 error. Like what you should really watch is that the error just reduces. And in some cases, you're looking at the communication protocol, you send so many bits. The best protocol with classically has some error probability, and with entanglement you can lower that. And so maybe not necessarily to 0, but you can just improve performance in terms of error or error exponent. And so Will and some experimental colleagues, they actually showed this for a practical channel in this paper here. So I think this is the last leg, so now I'm going to multi-parted entanglement and multi-user communication, because again, this finally is the part which is really less known. So multi-axis channel is kind of the simplest, historically the first analyzed example of a multi-user channel. You have two senders who act separately, who have independent messages, but for some reason they use the same system to communicate, or the same system in the sense they prepare inputs to something, which then interferes those inputs in a crazy way. And so the output depends on both of those inputs. And if it's a quantum channel, well, okay, it's a quantum channel acting on two quantum systems and spitting out one quantum system. That goes to Bob, and then Bob should measure and try to recover with high probability both the messages of LS1 and LS2. And so what happens if there's entanglement? And so yeah, what you have to appreciate is now the entanglement can be of all sorts of different kinds. It could be between the two senders. It could be between one sender and the receiver, or between the other sender and the receiver, or it could be a tripartite entangled state. I mean, we know that in multi-party entanglement, there are qualitatively different ways in which the parties can be correlated. And so I want to show you the example of the binary adder channel. So this is the classical binary adder channel. So this is the two inputs are just classical bits, and what the channel does is just adds the numbers as numbers. So the output is 0 and 1 added, so it's between 0 and 2. And so it's entirely deterministic. That's the beauty of it. The channel is deterministic. So like if you had only one sender, if this was one party here, you had no secret. You can just prepare you can equally use all these three symbols and you get log 3. Since they act independently, each of them acts as noise to the other because each of them doesn't know the message of the other one. And so the capacity region, so the pair of rates at which they can communicate is this one. Both of the rates are bounded by 1, because if one party just quiet, then the other one can send a bit. And the rate sum is 3/2 rather than log 3, which is bigger than log 3/2. And so this is the capacity region, this picture here. And you can ask yourself, so what happens if we add entanglement? And so yeah, well, first of all, before you do this again, the baseline, so famous result of Altswede, if you have a general classical channel, then the capacity region can be given in these Shannon theoretical terms, and it's a single letter formula. And okay, you can generalize this also to quantum channels, which I guess is the second reference here by myself. So being a PhD student of Altswede, this was like natural that I would look at this problem, I guess, in quantum. Yeah, so for a general channel, unfortunately, we only have this kind of, again, this kind of regularized formula, but each of them is a kind of a Shannon theoretical characterization with 3 bounds. So each rate is bounded and then the rate sum. And so, yeah, so I hope, well, maybe at the last minute, I will be able to come back to the classical adder channel and to classical multi-axis channels. But I want to discuss a bit of some historical work, which was never published, with Gleb Klimovich, who was at the time, I think, a student of Tom Cover. And now I lost a bit track of him. So he came up with this example of the quantum binary adder channel. So what is that? Like, how can you add qubits? Well, you don't. Actually, the channel action is noisy one. So you take 2 qubits, and the channel action just permutes them randomly. So it gives you either rho tensor sigma or sigma tensor rho with equal probability. So for classical bits, that's equivalent to the action of the adder channel, right? So if you give you a bunch of bits and I just randomly permute them, that's equivalent. Then the only information that survives is the number of ones. And that's the adder channel. So this is like, there was this idea, that's my quantum model. And in fact, this is not a bad idea because we proved that the capacity region of this without entanglement is actually like the classical adder channel. It's the rate individually bounded by 1 and the rate sum is 3/2 maximum. And so we couldn't do the regularization, but we think it's the same. And so then we played around with different kinds of entanglement. For example, sender-sender entanglement. So that's kind of, yeah, a priori you would think, why would it be helpful? But of course, in this case, with action of the channel, it's very easy to see why this is good, because those belt states, they are permutation invariant. It doesn't matter if you flip them around. And so you can do a dense coding protocol where each of the rates is now bounded by 1, but the rate sum goes up to 2. So that means both of them can actually send 1 bit simultaneously with no interference. Beautiful. You can have a GSZ state. It's even better. So each of the rates are now bounded by 2, because we actually can do dense coding each of them when the other guy assists. And the rate sum goes up to 5/2. And then we even played with sender-receiver entanglement. And again, you get a different capacity region. So like the type of entanglement expresses itself in different kinds of advantage, but it's not a number because it's like the region changes, the shape of the region changes. Even though in our case, the most significant thing is the change of the rate sum. And so, yeah, so for example, this kind of model where we send a receiver entanglement, this one we later on looked at with, actually, I forgot to put the year here, with Minshu Shea and Igor Devetak. We looked at the general quantum multi-axis channel with where each sender is entangled with a receiver separately, and we gave a multi-letter formula for the capacity region. So we don't know in this model which channels have a quantum advantage. This is completely, it's very hard to compute this region even in very simple cases. Yeah, so going back to the classical channel, so this is only in the last few years that various groups have realized that even if you have a classical channel, entanglement can help you communicating, I mean, in rate terms, communicating through this channel. And so this is surprising, and maybe this also explains why it took so long for people even to consider this, because of Bennett. So it's actually his fault, because he had studied too much the point-to-point channel, and what they had found is that a noisy classical channel has the same Shannon capacity as the entanglement-assisted capacity. And there are different proofs for that, but it led to this kind of very strong idea that entanglement doesn't do anything to classical system. Maybe, okay, then we found, okay, it does something to the error probability, but the Shannon rate doesn't change. And so for multi-access, it took a while. So the history, I'm happy to explain it in the coffee break. So I quote here an unpublished manuscript of Yannis here with myself, that he actually eventually took some part and made into a paper. And then a very, very cool paper by Felix Leditsky et al. From 4 years ago now. So where they show that certain classical multi-access channel with 2 senders and 1 receiver, the capacity region can increase if you have entanglement between the senders. And so the way you do this, and the way all the subsequent work that also some people here made a kind of more information theoretical analysis, the way you do this, you appropriate Bell inequality, you appropriate a non-local game that is played between the 2 senders, and that somehow winning that game helps you communicating. So I'm not going to explain that here, unfortunately, but yeah, just mentioning that while working on this with Yannis, we also stumbled across some papers of Quack and Shore, where they did this for a much more complicated case of interference channel. Anyway, so the effect is tiny. So like you have here the capacity region, the entanglement assisted capacity region of those examples they're engineered so that it becomes a square. You reach this corner point here where both rates are maximal and the sum is maximal simultaneously, and you can't reach that point unassisted. But the advantage is tiny, so you can't see that here because this is where our zoom is. I zoomed in here just to show that you don't reach this corner point. So you have to look in the slides later. Yeah, so for example, going back to the binary adder channel, we don't know if that one experiences that sort of entanglement assisted advantage. I mean, not so extreme, but something. And that's a not completely meaningless question, because Fauci and one of his collaborators, they showed last year, published this year, that if you have no signaling correlation between them, the 2 senders, then the capacity region of the binary adder channel is increased. And it's a bit of a complicated calculation, but we don't know exactly what the amount of increase is, and we don't know whether this can be achieved with pure entanglement. But yeah, this looking at this no signaling correlation because of the Bell inequality, because you have this non-local game played between the players. That gives you the idea. Maybe I should ask as a resource not the entangled state, but this correlation. So it turns out, so this comes now from this unpublished manuscript that I have with Yannis, you can construct channels with input size n, so each of them like has log n information content, and output also size n times n, where the unassisted capacity region looks kind of almost like a triangle. So the individual rates are bound by log n, and the rate sum is log n plus some lower order thing. And assisted by not assisted by entanglement, assisted by no signaling correlation, you can reach again this corner point. So the 2 senders can communicate maximally without interfering with each other. And that is using XOR, so-called XOR games. It's kind of a class of non-local games that are very well understood in the bipolar setting. And so these are my conclusion slides. So other things that came to mind while I was preparing the slides, and which I don't have time to talk about, and also in previous attempts of giving this talk, never had time to talk about. So also if you're in very adversarial channels, so if you have a jammer trying to prevent you from communicating, entanglement can have dramatic entanglement advantage, raising the capacity sometimes from 0 to something positive. There is the whole field of entanglement-assisted quantum error correction. So this is not so much an improvement of resource, because you need the entanglement anyway first to make error correction. So if you do the amortization of the benefit minus the cost, it's not necessarily better than an entanglement, well, at least not Shannon theoretically, but sometimes the codes are easier, they're simpler to implement. And so the last thing I want to say is more of a philosophical reflection. Where do these the entanglement advantages come from? And especially the last ones, it's very suggestive that there is this link to a game. And in fact, I think this is no accident. I think that the fact that you have that you have an advantage has to do with coordination. And we've seen this also in much more complex settings. I actually have a survey paper with Giannicola Scarpa and a few other people, where we look at general Bayesian games. So this like Nash equilibria with correlations. And so we can show, we and other people can show that having entanglement or other such non-local correlations can produce new equilibria, which are inaccessible, which are not equilibrium points of the game without this correlation. And in fact, you have quantum equilibria, which are not classically correlated equilibrium, for example. And so this is sort of a more general way of looking at it, that the correlation, why we get an advantage of communication, is not so much that the entanglement somehow spookily communicates something. That's a silly idea. What it does is coordinates. It's a kind of correlation that coordinates better than just classical correlation. That to me seems a much more fruitful way of thinking about it. Okay, and I stop here. So sorry for running over time a bit.
Yeah, thank you very much for this very interesting talk, and which was enlightening and gave rise to questions, I hope. So I think we can still ask some questions, maybe 2 questions or so. And do you have any questions?
At the earlier part of the talk, you had a noiseless channel with noisy entanglement.
Yeah.
You had this delta, which looks like a dual of coherent information of a channel, because instead of maximizing over a state, you maximize over an encoding channel.
Yeah, exactly. Some kind of pre-processing. It has to do with the fact that the coherent information is not monotonic, so it's not. It has data processing only on one side.
Yeah. Now, in the case of a coherent information of a channel, for the class of degradable channels, it single letterizes. Right?
Yes.
Does it single letterize here?
Yes. I mean, I believe so. I'm thinking about where this might have been written, actually. Yeah, you would have to have a notion of degradable state, so that which is easy, right? So you look at you have rho AB, the density matrix. You purify it with a third party, and so then rho AB should be degradable to rho AE. There should be a map that from B to E that pertains to transform. And so for those, I think the pre-processing is not necessary, and then you get for those you don't get an advantage by doing this pre-processing. I think that's the story.
Okay.
So that it should be true, but I don't know if it's actually said in those words in any of those many papers. Okay. Maybe in the last one.
If there's time for another comment or question, or
very nice
maybe
question.
Quickly, because I mean, this is I think it's an interesting question of when entanglement helps. As you said, it's really not obvious, and we've shown that in broadcast channels, it doesn't help entanglement between receivers doesn't help. And then it was even strengthened recently by Fauzi and Fermat. They showed that even non-signaling correlation doesn't help. And then some people ask me, well, we know that there's quantum illumination, and in sensing it helps between sensors. So it looks strange that it shouldn't help in communication. Do you have any thoughts about?
I think it's mysterious. I think it's a lot of unknowns there. Exactly like broadcast. I should have mentioned the broadcast channel, because it's sort of operationally justifiable why receiver correlation doesn't help, because there's nothing afterwards. They just report. But yeah, what's the advantage of sender-receiver entanglement? And yeah, what are the situations in which it happens? First of all, that's from the communication point of view, right? And then for this illumination, it's the same kind of question. Okay, we know some effect happens if you have really high quality entanglement, but if it's very noisy, where does it disappear? Like it's the same sort of question. Is every entangled state, even however noisy, still useful for something? I think it's huge terra incognita.
So I think we'll have one question by Bulat and then. Okay, Janis. Okay.
Well, okay.
Yeah, so I have one question, one comment. So in this this work that I coupled out from our earlier work, it is actually an all or nothing advantage even.
Yeah, exactly.
And I had some follow up with Stephen where we showed some kind of exponential separation between sum rates. So it is not just you don't get just a very small piece, but depending on the model, you can get really large advantages.
Thanks for reminding that. I should have said that. Yes, it's a slightly more complicated model, but you get a huge advantage.
You pay with it with model complexity.
Totally, yeah.
But I had also a question regarding this work you had with Debbie Long and Matthew Williams, and maybe others, which I forgot. You said they did some follow-up work where they tried to investigate.
So what we could show was basically just a one-shot separation. One use or a few uses of the channel, we get a quantum advantage because we're just comparing the independence number with the protocol that we came up with. For the Shannon capacity, you have to look at the limit of the independence numbers. And so that was their follow-up work. They actually show the separation between the asymptotic zero error capacity and the asymptotic entanglement-assisted capacity. And then there's a paper by Burman and al. In this Amsterdam group, where they showed even a really sizable gap, like by investigating specific graphs. I mean, like you have to know a bit the literature of zero error capacity, so you can learn about specific graphs which are promising, and they did that.
Are you aware of any work where they try to map this to some application?
Well, I would say the one of Will Matthews in the end. So like what the realization was that it's not so much the zero error, because that is exactly what makes it difficult to justify an application, but it shows a reduction of error. Like, I mean, when you application is maybe not zero error capacity, but in application people pretend sometimes to care about reliability function, and that is affected by entanglement.